Good evening. Very good, very good. Everyone is here. And welcome to the 2022 Von Kármán Lecture in Aeronautics. We're happy that you could join us tonight. I'm Fred Hadier, the chair to the AIAA Honors and Awards Committee. This lecture is named in honor of Theodor von Kármán, a world-famous authority on aerospace sciences. This award of his lecture honors and individuals who has performed notably and distinguished themselves technically in the field of aeronautics. It is my distinct pleasure to introduce you to the 2022 Von Kármán lecturer, Professor Kathleen Howell, a very long-time colleague, distinguished scientist. Professor Howell is the Schuler Distinguished Professor of Aeronautics and Astronautics in the College of Engineering at Purdue University. Professor Howell's technical research focuses astrodynamics in complex gravitational environment. She has successfully applied these methodologies to various flight missions and mission proposals. Her contributions include mission planning and trajectory optimization, station keeping, and maneuver design, low thrust applications including small satellites, and the development of interactive virtual capabilities for complex mission scenarios. As a principal investigator, Professor Howell has obtained numerous grants and received various awards related to her research program, as well as in recognition as an engineering educator. She served for many years as the editor-in-chief for the AAS, Journal of Astronomical Sciences. She's also a member of other editorial boards. Professor Howell is a member of the National Academy of Engineering, the American Academy of Arts and Sciences, and the International Academy of Astronautics. She's also a fellow of both AIAA and AAS. She's involved with various other organizations within the international aerospace and astrodynamics community. She earned her bachelor's degree in aerospace engineering from Iowa State University, her master's and PhD degrees in aeronautical astronomical sciences, both from Stanford University. She's quite an accomplished person. Please note that after her lecture, we will have a question and answers. I now invite Professor Howell to come here and start the lecture.
Thank you. Thank you, Fred, very much. I very much appreciate that introduction. And I just want to start by saying I have been at this a long time. And believe me, it is not that often that you get this kind of a forum to talk about orbital mechanics. So I do appreciate it. I want to take some time today and talk a little bit about not only the cislunar space, but also how to move vehicles around in that environment. And everything I talk about today then, I want you to think about through my lens of having to deliver vehicles to wherever you all need them to go, and lots of times to return them as well. So I'm going to start with this particular image that I borrowed from our colleagues at JSC, because I think it's a good one in order to start talking about the definition of cislunar space. Now, some might say that it starts from the surface of the Earth out to lunar orbit, but not everybody agrees on the boundaries of those regions. For example, some would like to say that cislunar space actually doesn't begin until we get past GEO. But nevertheless, this is a good place to sort of describe it, as well as the fact that the libration points are also in this image because they play a key role. So the collinear points are on the Earth-Moon line, of course, with L1 and L2 on opposite sides of the Moon relative to Earth. L4 and L5, the equilateral points, are also relevant and are in this image. Now, with those points there, myself, I like to say that the boundary, the outer boundary, also extends beyond lunar orbit out to that L2 region, because there's a lot of activity that happens there, there's a lot of interest there, and that region affords us the opportunity to view the backside of the moon. So, given that start, I want to make a couple of observations. First, this is a very large volume. So although the image here looks flat, it's actually a sphere. That's a lot of space. And when I think about then having to develop transfer options between different destinations within that kind of domain, it's actually quite a challenging problem. So the question is, from my perspective again, what do we actually want to do there? And we've been talking a lot, particularly today, there's been a lot of discussion about developing the space infrastructure for this particular region. And that means, for example, that includes NASA's Artemis program, the Gateway Station, which is going to end up being in a location that might serve as a transportation node. We've also got many of you in the audience are from commercial organizations that are expanding into this particular region. And that means that you're also interested in building a strong economic base for operations out there. And those activities are also a focus of many of our international partners. Down in the lower right on this particular slide is also the CHIPS concept from AFRL. They're interested, of course, in the space domain awareness in this regime, and I think those are halo orbits down there. And so how do we place vehicles in locations in which we can accomplish that? Now, all of these, including CubeSats and SmallSats, are really part of this entire vision. The CubeSats and SmallSats in particular are important because I may need to move them wherever throughout this entire region, and they're likely to be propellant challenged. So how do we accomplish that? How do we have access to multiple destinations, do servicing and testing from my particular view? Now, it's also important then to say, in order to build that infrastructure, what kind of capabilities do we need? I'm borrowing here from some of my colleagues at the Aerospace Corporation, who a number of years ago did an analysis of what are the important capabilities that still need development. Of course, this one was important to me because it includes interorbital transportation right at the top of the list, or at least close. Since then, many other both organizations and individuals have looked at this and developed lists of what things need to be developed and what are the timelines. There's also been, in those particular cases, different focus sometimes, and they don't always include the orbital aspect. But it is important to recognize what we're going to have to do and how we're going to have to be able to move those vehicles around no matter what we do in order to further sort of develop this whole entire regime. Now, that brings me to another question, which an interorbital transportation or a transportation network, what does that actually mean? Now, there's a couple of images here which are interesting. The one in the upper left there comes from Marshall in 1970. There's a trajectory in there to talk about a mission to the moon, but really what at that time they were focused on with this particular image was the hardware that they needed to make this occur. Jump ahead to the lower left, that's 2012. This is from NASA Glenn, and again there's a trajectory in there, but they were talking about developing a propellant infrastructure for that region. On the upper right, that's a trajectory concept for Artemis 2. And that's still forthcoming. But when I think about moving vehicles around in this particular domain, those are not the pictures that come to mind to me. I'm much more likely to think of the one in the lower right. Those are actually orbits near L4 and L5, those equilateral points. And those are the kinds of orbits that I may have to deal with in order to actually deliver the kinds of capabilities from the orbital perspective that we need in this domain. Now that means that we need to create a framework, and the framework is really built on this region of space, and in this particular image, looking at it from the perspective of a rotating reference frame where the Earth-Moon line is fixed, also makes the equilateral points or the libration points very, very clear. And so these are important locations because they actually help deliver the underlying dynamics that is important as we move through this region. They sort of guide the dynamical flow and the structures that are available to us. So it turns out that mathematicians and astrodynamicists have learned a lot about that flow in the last couple of decades. And we continue to learn there's more types of solutions, understand better how the solutions interact with each other, what the broader characteristics are, and probably most important to this particular group is how to leverage them in order to accomplish the objectives that we pursue in this domain. We mustn't forget, however, as we're doing this, that the Earth-Moon system and its libration points are actually buried within the Sun-Earth system and its libration points that you see here. So when we talk about the Sun-Earth, we sometimes collapse the mass of the Earth and the Moon into one point, take that mass with the Sun, and have a three-body problem: Sun, Earth, Moon mass, and spacecraft, similar to when we work in the Earth-Moon regime and we talk about a three-body problem that is constituted by the Earth, the Moon, and a spacecraft. So in both systems, we have three-body systems that are relevant. In this particular image, for example, over there on the far right, in the Sun-Earth L2 point, is where James Webb sits today and is sending back those stunning images for us. There are some scenarios, particularly for some small spacecraft, where we actually have to work in a four-body model: Earth, Moon, Sun, and spacecraft. I'm not going to talk anything about those today. I'm going to focus mostly in the Earth-Moon system and just with our three-body problem in that system. But it's important for us to remember that that's there because that additional either perturbation or assistance from the Sun may be important for different missions. So in order to design in this regime, there's actually a variety of different kinds of mathematics that we can use. And there's more than this. This is just a reflection for me of what we can actually do. And so these 6 pictures actually represent sort of an approach that almost every orbit dynamicist that works in this regime takes, where the top row there is basically delivering what are the building blocks that I can use in order to accomplish whatever objective that I may have. So, for example, the building blocks to create my inner orbit transportation network, for example, means that I first have to know what everything is that's available to me, including the periodic orbits, and characterize them. Now, anybody in my field knows that Poincaré told us in the 1890s that this was the first thing that we should do, and we should do it exhaustively. And I guess now in the last couple of decades, we've actually been following through on that early recommendation. But we've also expanded it now so that we have other knowledge about other types of orbits, for example, the quasi-periodic ones. So it's important for us to know that there's lots of different types that we can leverage. They can also come from any kind of model. However, when we get into some orbits that we might be familiar with, for example, halo orbits, we still don't have in 2022 an analytical set of parameters that we can use to describe those. So that makes it more challenging. And we haven't yet come to the point where we can categorize them and offer accessibility, meaning there's a set of building blocks that if you have expertise in that area, you will know what they are. But how do we afford that to a lot of folks that are going to be trying to move their vehicles in this regime and don't have the same access as the researchers do? So that's also something that's a work in progress. Then there's also other structures in the system that we can also leverage. That includes things some of you have heard of, I know, manifolds, for example. There's also relationships between structures, and there's also guiding behaviors that we know that can help us. Some of you may know the zero velocity curves or Lagrangian coherent structures sort of guide the paths. And when we put all of these together, that sort of gives us our entire set of building blocks that we can call from, the ones that we can pick out what we need to do. And that takes us to the second row, which is actually representing a range of strategies that we have in order to render the links or the pathways in order to accommodate whatever the goal is for a particular vehicle. Now, there's a lot of different kinds of tools that we can work with there, but the important thing for most of us is that moving around through the cislunar region can be very expensive in terms of propellant. So we need to leverage all the dynamical flows that we possibly can. So we have to understand them, we have to recognize how one may influence another. And a lot of the behavior is non-intuitive to those of us who are familiar to working closer to the Earth. So we have to be able to leverage that. And then the development of numerical capabilities, which has been a real, has taken many steps ahead in the last decade or so. But there's still a lot of work to do in getting algorithms for fast responses that can still work in this sensitive dynamical environment and deliver sort of a path that is going to be useful. Not to shortchange any of those algorithms, but the general approach has been to design in the lowest fidelity model that we can, and then transition that to the higher fidelity model that's for operations. The goal being to preserve the characteristics along the way. That is an ongoing research problem to make sure that we can do that consistently and we can, again, deliver exactly what we want. So those are some of the ideas of the kinds of strategies that we need to put together. We have to know what the building blocks are and then figure out how to put them together in order to accomplish the objective. So I'm going to start a little by giving some examples. And the first thing I'm going to do is put this up. I don't want you to read it, but the first step on finding the building blocks was to understand what all the periodic orbits are. This is an example of a small subset of that category of periodic orbits and all the possibilities that may exist just in that one little category. I think many people in this room are probably familiar with the top two in this chart that are Lyapunov orbits, which are planar, near the libration points L1 and L2, and I've heard today halo orbits mentioned numerous times. Just as a reminder, here's some images of what those guys look like. So this is in a restricted three-body system, which is the lowest fidelity model that I can use where these types of orbits exist. These are examples of the planar Lyapunov orbits. They are near the L1 family's on the left, L2 is on the right. Those different colors mean that these orbits are at different energy levels. I have to be cognizant of the energy level. I can't just pick one of these at random. Now this then is an example of some of the halo orbits. This particular case, if you look carefully, you can see on the left the moon there in the center. These are what are called southern halos. There are mirror images across the Earth-Moon plane. But these also come in L1 and L2 types. So the L2s are on the right, the L1s are on the left. And when you look at these, one of the things that you might observe is that some of them go very close to the moon, which of course is something that we've tried to leverage already. But even though they go very close to the moon, in some cases they may have an altitude as low as 3,000 kilometers, but they can also have an apoapsis altitude that's as high as 100,000. So that's something that we have to be also aware of. Now, I selected this set, which are the ones that spend most of their time below the Earth-Moon plane, because this includes the set of inner HOs, which a lot of you have recognized and talked about, particularly within the context of the Gateway program. So look first there on the left. Those L1 and L2 families are there again. This time, though, I included the colors for the different energy levels. And these plots were done much more recently by my collaborator, Diane Davis at JSC. And you'll notice that as they got closer and closer to the moon in that picture on the left, the L1 side, those apolloons get way larger than 100,000 kilometers. That was why, when NASA selected the orbit that they're going to use for Gateway, they actually went to the L2 side, because those apolloons are much more within a usable distance. In the middle picture, you see the entire family of those orbits. What's called the near rectilinear halo orbits are actually the ones that are in that region between the two white orbits. Those are the boundaries of that region that define the inner HOs. Some of them go very close to the moon, some are quite much further away. These bounds are determined by their stability, but the reason for the name is because, as you can see, if we've got the Earth-Moon line there, and you're looking below the plane, that the one that was selected for Gateway is very close to the white one on the left, and it's almost completely out of plane. And so it's almost, 90 degrees to the Earth-Moon plane, and that's one of the reasons for the name. But that's the one that was selected, and when I'm thinking of this as either we need to get to it or we need to use this to go to other places, I may have to leverage a lot of different kinds of trajectories in order to make that happen. Now I'm going to show some examples here, and I just picked some that utilize some of the building blocks from the top left and a couple of the tools that we have down on the bottom. It doesn't make the difference so much what the example is. But I've got here an example that includes two Lyapunov orbits, one on the L1 side, one on the L2 side, and they happen to have the same energy level. I also picked a direct prograde, which is actually a moon-centered orbit, and I want to link all of those guys together. Now, the other type of building block that I have in order to accomplish that is that all of these three orbits are unstable. So that means that they have manifolds, which some of you have heard about. These are what the three families may look like. I'm picking one out of each one. All of these orbits are unstable. We'll pick one out of all three of them that has the same energy and look for their manifolds. Now, all that the manifolds is just that if I pick this orbit, and this happens to be an L1 Lyapunov there in the green box, that there'll be flow that naturally moves away and asymptotically approaches as well. There's no maneuvers or anything, but I can leverage that flow possibly to get into and get out of that orbit. So we're going to use that information along with some other tools and pretty quickly come up with these two kinds of orbital links. Each one is a result at a different energy level where I can move from L1 into the direct prograde orbit, and then I can move to L2. This is all accomplished this is completely ballistic. I can also go back the other way, so I essentially can all use these building blocks to create other orbits that might be useful. So this is just an example of how to put all those pieces together. Here's some other examples as well. Now these only have two orbits at a time, but they also indicate how many other orbits are out there that might also be useful. On the left top, we have some vertical orbits. Down below, we have axials. To the right are those familiar three-dimensional halos, and in this particular case, we're just linking two halos together. Again, this is ballistic, and there aren't any constraints on it, so you all might have some constraints to add as well. But we put the pieces together, and we can accomplish what the objective might be. The other thing that I mentioned that was truly important was the developments that we've made in algorithms so that we can take those examples that come from lower fidelity models and we can transition them to ephemeris models in these particular cases in a way that these were just inserted into GMAT. There are the lower fidelity models that are underneath the black ones, and the black ones are in the full ephemeris operational model, and you can't really tell the difference. So we can do these transitions. We need to do them. We still need to develop, in some cases, more capable algorithms, because right now sometimes you have to put intermediate models in as well. But that's promising for whatever we might have to, destinations we may have to go to and return from. These particular examples, however, also were focused on maybe I want to stay in the vicinity around the moon. For whatever I want to accomplish, maybe I have a depot there, maybe I have some other kind of effort that I want to make, maybe I have some satellite there that's doing SDA. But I wanted to stay in the region around the moon. There's a whole other set of orbits that I can use if I actually want to tour the entire system. So those are resonant orbits. There are some of those that stay close to the moon vicinity, but there's also a lot of them that go throughout the entire region. So here's just some examples, a subset of those that we can also use to sort of move throughout the entire cislunar space. So if you look at the locations there of the Earth and Moon, if you can sort of see that on the slide, might have to squint. These are the possibilities. The gray ones are the ones that stay in the Earth to Moon plane. The blue ones are all three-dimensional, and there's a lot of others as well. Now, this was not just an academic exercise, actually, either. Already, a lot of these have been utilized. For example, in the first column on the bottom, there's one that's called 3-to-1. One of those blue types was actually leveraged for the IBEX mission, which launched in 2008. The column on the left, the one in the middle, is actually that 2-to-1 that you see there is actually, one of the blue ones was leveraged for the TESS mission, which launched in 2017. There's also been a number of other cases where they've actually been explored. Besides just using them for a particular mission, though, we can also use them as links in order to connect things, especially if we want to move around the entire system. This, for example, was a response to say we might be interested in a type of trajectory that might move back and forth between the moon and regions near the Earth. This looks like an isolated trajectory. There's actually an entire family of them. They all go about the same type of distance from the moon, but they all may approach at different distances relative to the Earth. In this particular case, we picked the one specifically that would just scrape GEO in this particular example. On the right is the view in the Earth-centered inertial frame, but I caution, in order to have the complete orbit, you need 2 revs in that view on the right. Again, it's completely ballistic, using the moon's gravity, but also leveraging the Earth gravity in particular when we get in that general region. That same orbit was transitioned to the ephemeris successfully. This is all ballistic. The view in the rotating frame is on the left. The view in the inertial frame is on the right. We did not put any constraints in here. On the right, the gray line, that gray thick line there, is the lunar orbit. I might also note that there are actually 2 orbits here. One is black and one is red, so we could sort of form up 2 satellites that would move around together. Now, they don't always stay at the same distance apart. Again, there were no constraints or anything in here, but one of the goals was to prove that we could actually do this. We also said, okay, we can mix and match as far as we want to go. So here we picked 2 orbits in the Earth-Moon vicinity, 2 orbits that went a lot further away. One of the requirements was that one of them had to go by the Earth. But the important thing here was, for each of these different types of orbits, how much time do they spend within a 30-degree cone from the Earth to the Moon? And also how we could phase them so that the vehicles in these 4 orbits might periodically return close to each other for various maybe data exchanges. Now on the left, in the rotating frame, it was pretty easy and didn't take us long at all to do this. The view on the right, though, is much more complex. So it was easier to actually work in this lower fidelity rotating type frame. Before I end, one of the things that I do want to mention, though, is the first Artemis mission from over a decade ago. And I want to do that because this is a master example of how to put all building blocks together and deliver exactly what you want. Now, this Artemis mission was actually an extension to the Themis mission, which had 5 spacecraft that were small, that were put up in 2007 around the Earth in order to investigate substorms, and they were very successful. At the end, they had the 2 outer ones. They were all in elliptical orbits, but the 2 outer ones were in, larger elliptical orbits. And the idea was to say, well, now that they're done with their main mission, we're going to actually send them to the Moon so we can get some other kinds of data around the Moon. But they had, a few drops of propellant. That was it. Now, the science for this mission was done at UC Berkeley. Mission design and mission operations were done by JPL and by Goddard, and we worked with the Goddard folks. But the key thing here is how they put the pieces together in order to leverage everything they had to deliver 2 spacecraft, actually without colliding, which was a non-trivial thing, who don't have any propellant left and how they're going to do it. Now here's an image actually in the ephemeris model of both trajectories. One of the satellites is in blue, one is in red. Gray there is the lunar orbit. And this is a case where it's viewed in the Sun-Earth system. So the line to the right is to the Sun. Now what they had to do, first of all, is they had enough, so they did a series in each case of perigee or apogee raise maneuvers. So start there close to the Earth. I don't have a pointer, but if you look really carefully, you can see one of the pink orbits that was where we started, where the apogee is about halfway to the Moon. This series of very small apogee raise maneuvers. They moved out close to the Moon, leveraged the Moon, and then both of them moved outside the lunar orbit where they could leverage solar gravity. So both of them leveraged that to replace propellant, and were able to get into the vicinity of the Moon. These are the images, though, that tell us what can happen in the Cislunar region. Look first in the image on the right. This was for the red spacecraft, but when it arrived in the Cislunar region, the orbit was very, very inclined to the Earth-Moon plane. So the first thing was to sort of use the natural behaviors, this is like a quasi-periodic orbit, use those natural behaviors in order to take the inclination to 0, no maneuvers at all. And then if you look over on the picture on the left, you spent some time then in the L2 orbit, then you used a connection through manifolds in order to get over on the right, spent some time in the right, virtually in the Earth-Moon plane, and then were able to, without maneuver, you could just, with unstable manifolds, just move more into that lunar orbit. Now at that time, this was harder to compute, and it's not like they had a whole family of options to choose from. But this was a way of putting a lot of those building blocks together in order to accomplish the objective, was to take 2 small spacecraft that virtually had no propellant and get them into, from Earth orbit into lunar orbit. Took a while, that's true, but It happened in 2010, so just over a little decade ago. And since then, we've been trying to think about how we might do this on a more consistent basis and do it in a more, I guess, with a strategy that's more well-defined. This was the first successful mission in the Cislunar region. And that's a good model for us and a good place, I guess, for me to stop because that's the idea. That's what we've got to try to do. So every time you guys tell us, well, we're going to put something here and we need to be able to get to another location in return, this is the way that we're going to be trying to think about it in this particular domain. So with that, I do want to thank all the years that I've been working on this. I want to thank all my former and current graduate students. But I've also had many astrodynamics collaborators over the years at NASA, universities, commercial partners, some of you I know are here, as well as international organizations. And we're still all working together to kind of, develop our own orbital infrastructure in order to enable all the types of activities that you want to have take place. So with that, thank you very much. I think, there you are.
Well, thank you very much for such an
Yes.
interesting presentation, talk, enlightening.
Thank
as
you.
always. So, the Institute Honors and Awards Committee takes pride in selecting accomplished leaders in aeronautics and astronautics who can share their knowledge through this lecture. It is my great pleasure, on behalf of AIAA, to recognize you with the Von Kármán Medal and a certificate. So I'll just get it and bring it here for you, and it's already there. Thank you so much. So let's do that, if you don't mind.
Okay.
And here is recognition to your contributions.
Thank
So
you.
I will take it here, and you just
Want to make
put
sure
this
that the
one
medal
over.
shows.
There we go. Okay, so there's a picture. Thank you so much.
Thank you very much, and I do take pleasure in receiving this from my longtime friend,
Well, thank
Fred
you so much.
Hadia.
It's quite an honor to be on the same stage with you again. Thank you. Now, I think that what we want to do is to start with questions, and if there is no other mic. Okay, so I didn't receive any questions from the audience. If you do not have any questions, we'll just call the night. We're very, very happy and grateful that Kathy was able to be here tonight to give us this presentation. Orbital, or the mission design that you've been doing, everybody has been using that. And in particular, the last part of the lecture was emphasizing multi-spacecraft systems. I think that we really were looking very keenly at using those techniques when we were going to move an asteroid through multiple spacecraft and bring it to L2. And it was much of the creative work by you and your students that really was the underlying, I would say, the methodology that was going to be used. So thank you so very much for coming here tonight. I hope you enjoy the rest of the ascent for the next couple of days. Thank you very much for this wonderful presentation. Let's give it a round of applause again.
Thank you.